moving on, we'll see why we looked at that eigenvalue, eigenfunction part in a while. But right now we take the same expression and we're going to differentiate it for the second time. So you take the double derivative of psi of x, which is nothing but derivative with respect to f of the first derivative. You will get I squared p squared upon h cross squared times psi of x, which is minus of p squared by h cross squared times psi of x. And why minus? Because I squared is minus 1. Remember that I is the square root of minus 1, so I squared is minus 1. So when you take the double derivative, this is what you get. And now we'll hold that over there for a minute. We saw that energy equals potential energy plus kinetic energy. Potential energy is V and kinetic energy is p squared by 2m. I just described how this happens in the previous section. Kinetic energy is mv squared by 2. You multiply and divide by m, you get m squared v squared upon 2m, and mv is your momentum, so m squared v squared by 2m is nothing but p squared by 2m. So that is how you get kinetic energy is p squared by 2m plus v. So you keep p squared on one side and push everything to the other side, you will get p squared equals 2m times E minus v. Now we take this p squared and substitute it in this equation we had. The second derivative of psi of x with respect to x equals minus p squared by h squared times psi of x, which is 2m into E minus v by h cross squared times psi of x. Now what we are trying to do is we are trying to bring it to the form of a linear equation in terms of psi of x again. So when you take the denominator to the other side and you split out this E minus v, and when you do all that manipulation, finally this is what you will get: minus h cross by 2m times second derivative plus v times psi of x equals E times psi of x. So this is very simple. It is just you take this expansion, you take the denominator to the other side and then you split this into 2m E minus 2m v. You take the 2m to the opposite to the new denominator and so on. It's basic math. So if this expression looks very confusing, if you're not able to identify how this one came about right now, I would encourage you, when you're going through the slides, to pause and start with this expression and try to work it out mathematically. It is simple math. So ultimately what we get is this expression in the pink box, and it is the time independent Schrodinger's equation for one dimension. Yeah, so moving on to why we are doing this. So the whole idea that we started out with was I need position and momentum to describe a particle, but according to what Heisenberg said, I will not know both with 100% certainty at any given point in time. I know one and I have this wave function. I want to be able to extract the second one. That was our objective at the beginning of this session. So all this derivation, all this math which we've been doing is to somehow get an equation such that if I know one quantity, I should be able to derive the second, right? So now you look at this equation in the pink box. So let us say I know the position for sure. Position in terms of x coordinate. We're dealing with one dimension, so there are no y and z coordinates, so the position is just a single coordinate x. So if I know the position, then I know psi of x, and h cross 2m, mass of course I know, so h cross is a constant. So I can bring everything to one side and I have E minus v times psi of x on the other side. So if I know the position, and psi of x will obviously be given to me, so E minus v is the unknown, I can obviously find out, and E minus v is kinetic energy. So if I have kinetic energy, I can get the momentum. Similarly, if I know the energy, so if I know E and v is constant, so if I know the total energy and potential energy, I can find out the kinetic energy, and if I plug in those values here, I can get back the value of psi of x in terms of position. So if I know one value, I will be able to get the other, so from this equation. So the whole point of the double derivative and eigenvalue, eigenoperator, everything was to get this. So again, after this we'll be looking at a time dependent case also. There also we'll get another equation like this, similar, but it will also have a time related term. The whole idea is I have the wave function and I have one known quantity, one unknown quantity. So the equation should help me derive the unknown quantity through sum operation, and that operation here is double derivative into h cross squared by 2m or whatever. So if you look at this thing which we first derived, because you don't know A, you cannot find anything out. And even though this is also in terms of P and X, momentum and position, and you know the psi of x value, because we don't know A, we cannot find out. Whereas here it is in terms of constants and the wave function, so if I know one value, I can find out the other. So in assuming that everything is constant, independent of space and time, this expression works.